what I thought I would do in the second talk is the I think I'm going to continue what I was doing this morning tomorrow. Instead, now I want to introduce a different description of infinity operads that maybe connects up a bit better with the other lecture series. Maybe look at infinity operads as inverted Segal spaces. So, so warm up to introducing this description, we can start by looking at how we think of infinity categories.
You want the lights?
Why?
Oh.
It's really.
Okay, so the way we can think about infinity categories as zero places. So we the simplex category delta, you can think of that if you want as the full subcategory of hash with the objects. After n, you should think that this is the ordered set 0 equals to 1 n, and then we can just think of it as a category generated by this graph. So it's object 0 to n, that unique morphism. Things we're thinking of a partial set inside category. And so using this embedding, we get a node functor from cat into functors from the option set. Right, so for now, I guess these days I have to say when I say cat, I actually mean one category, it's not infinite categories. And so this is just a normal norm of a normal category, so I can let's see degree m is set of functors from C, which is to say it's the set of n composable morphisms in C. And this node functor is fully faithful. And there are several ways of characterizing the image, but one way is to use the Segal condition, which says that so this is set X is the essential image of this functor, as X such that if I look at the set level n is isomorphic to the pullback of x1 over x0 over x1. Pullback of n copies of x1 over x0 via the match we get by looking at the inclusions of the one element set I and sets of the ordered sets of the form I minus 1 I into here. We go to 0, the set of objects. 1 is the set of morphisms in the category, then we have the place maps, D0 and D1, which give us the source target of the morphism, and then we have the degeneracy, which is some empty morphisms. And then if we look at x2, then what this Segal condition is saying is that that's the set of composable pairs of morphisms. That's what that's photo point master. I have two point in x2 is two things from x1, such that if I take the source of one, target of the other one, they have to agree and so. And so let's exclude this to compose with interesting morphisms. That used the first and last case method, and I have the middle one, P1, going back to x1, and that's telling me how to compose morphisms. Okay, so we can think of categories as a full stop category of simple sets in this way. And so the last one is the delta that is showing up here. So we can think of the object of delta, so these things like this, as kind of the shapes that we can compose along in a category. And then the morphisms encode of the composition operations. For example, we have the map from 1 to n, something 0 to 0, and 1 to n. They'll tell me how to if I use along that, I get a map of sets that tells me how to compose my string of n morphisms to get a single one. But then we also have the morphism delta can encode decompositions of these diagrams and shapes. So we have, or maybe I should so of the shapes. So for example, we have the map 1 to n given by 0 goes to I minus 1 and 1 goes to I. And that's going to take my list of n morphisms and project out the ith element in that list of n morphisms. And then the point is that we can use this.
Sorry,
Yeah.
can you put the board up? Or the books down? Yeah, maybe the box down is a smart idea.
Sorry? Okay, and then the point is that we now have a definition we can generalize into the setting of infinity categories. Here's the first definition of a Segal space. Segal space is a number of next one close off here. S. I'm going to use this old-fashioned notation of the infinity category of places. The group lines. Or that other thing that I'm not going to say. I'm lucky that last isn't around. Such that we have the same condition as before. And if I evaluate with n, then I it's already filled out. Should be equivalence in the reports using the same maps as up here. And so this object is again, you can think of this thing as encoding the algebraic structure of an infinity category. In the same pattern as above, it's here we have that x0 is the state of objects, x1 is the state of morphisms, and then some crystal maps give us source and target homomorphism, identity morphisms, and compositions of a composable pair of morphisms. And then, well, I'm just spend too much time on this, but basically you can define open depth. Fully faithful in the sense of subjective. Morphisms between Segal spaces. And then we get correct infinity category of infinity categories. We should invert these fully faithful in the sense of subjective maps. Then let's prove that we can do that. We do this translation by restricting to full subcategory of the Segal spaces. So, which is, I'm also not going to define, but the point is that this is the property a Segal space can have, which basically is, it tells you that the space that you have in level 0 is like encoding the equivalences in your infinity category. So, but the point is that this is just a property, and so just looking at the full subcategory of the things that has that property gives you the correct homotopy-coherent infinity category. Okay. Right. So the point of going through all this is that now I want to do the same thing, but for operads. So we have quoted about the thing that's going to replace delta. So we can think of delta here as arising because it consists of the shapes that I can compose in a category. So now I want to define so-called dendroidal category. This is, yeah. So this points at the basic composable shapes for an operad. These are going to be these. If I have, in the sense that I had before, if I have a multimorphism, I have some more. So I have an iterated diagram like this. But if you keep going, it kind of builds up into a tree, and then in an operad, there's supposed to be a unique way of composing any such tree of operations to get at a new operation in the operad. We want to define those trees, which is going to be this so-called dendroidal category. And this, the word dendroidal has something to do with trees, and that's where it comes from. I don't come from a civilized country, so I never had to study Latin or Greek, unfortunately. So we want to define the relevant kind of tree for this this notion of composition. Then we'll come also with a notion of subtree inclusion. And then define, given one of these trees, a kind of free operand in the tree. And then we can define over here, in the category case, we could think of delta as a full subcategory of cat on these generating shapes. And so we can do the same here. We can define this dendroidal category omega as close-up category for instance sense on these objects. Then we can actually give a more concrete description of what the mass data look like. Okay, well, and then I'm going to describe use this category to describe the thing we Operads on certain equations.
Sorry, why is the notation? Why do we use the omega as notation? Is there any reason, or is it just
That's I don't know if there is a reason for it. It's just conventional. I don't know if there is a Greek word for trees that starts with omega or not. Right, so we have to think about trees. And it's very easy to give very complicated definitions of what a tree is. But I'm going to try and give a simple one that I believe is due to UCPH. So the idea is we can think of a tree. Well, so there's like lots of different types of trees, and there's like different ways to describe them. So I should say my trees are going to have a root. The sticks, so they're oriented trees. And then they have vertices. They have leaves, so then there's no dot at the end of the there's no vertex at the edge of the root or at the edge of the leaves. So that's my convention. So sorry, there can be a dot, but that means that I have like a nullary operation coming in there. So that's like a vertex with 0 incoming edges. Right, so then we can think of a tree. My diagram the following shape. So E diagram of sets. So E here is the set of edges. And V is the set of vertices. As I said before, I don't think that there's not supposed to be vertex at the like outer edges of my tree, unless it gets to another question. But then V star is the set of vertices plus chosen increment. So each of these vertices is supposed to know which edge is outgoing, and the rest are incoming. And like the outgoing one is the one that brings you closer to the root of the tree. And so I have this I map, which is going to send my pair consisting of about vertex and edge in edge. And then U is going to take my V and projecting and forgetting my edge and sending it to the vertex I have. And then O is going to take a vertex to its unique outgoing edge. Okay, so this diagram encodes the full structure of the tree. And then the point of the definition is that we can actually describe trees, characterize those diagrams like this, like corresponding to trees. We can find a tree in the diagram. Sense. Shape. Functionality. O should be injected. which says that every edge is outgoing for at most one vertex. You can't be the adjoint of several vertices. That I should be inductive. So an edge is incoming for at most one vertex. And there exists a unique edge R, which is called the root, which is not in the image. Right. There is a unique edge that is not incoming, in some vertex. And then we want to say that every edge is connected to the root by a finite number of vertices. So we can say that for us, we define a map sigma from E to E by taking sigma of the root through the root, and then sigma of another edge x. So if it's not the root, then I inverse of x is well defined. There's a unique pre-image of x. And so I can take U I inverse of x, which is to say, if I start with an edge, I look at which vertex it was incoming from, and then I take the outgoing edge of that vertex. And then the condition is that for every edge x, if I iterate sigma enough times, I have to end up at the root. Yeah, and then this notion of tree also comes with a very natural notion of morphism between trees, which is going to tell us what subtree conclusions are. That's going to be the diagram. Yeah, there's only one map on edges, and then there's a map on vertices. And then this middle square has to be a full map. And so that tells me that a vertex has to go to a vertex with the same number of incoming edges. So I'm not allowed to mix up the different parities of vertices. And so why do I call this a subtree inclusion? Because if I'm not misremembering, it just follows from the axioms for a tree that if you have this setup, then it's automatic that F and G are conjunctive. And you try and think about what these conditions means in the case of a tree. I think this unpacks to a very natural notion of what a subtree inclusion is supposed to be. I have to send every edge. My subtree is given by picking some collection of edges and collection of vertices, but then they have to fit together into a tree. And that's kind of what the definition says. Then I'm supposed to, that covers step 1 in my list here. And so now I want to start with one of these trees and define an opera. So given a tree, an operad, G. So it's objects or colors on the edges of my tree. And then multimorphisms from and this is the same with single dash y will be the collection of subtrees of T with x1 to xn its leaves and y to and then you have an action by commuting the leaves. That's also kind of baked into the definition. So and then the composition, right? And I should say there is up to this reorder, there is a unique tree if there either there is a single subtree with these leaves that root or there's none. If you can't have like non-isomorphic ones. Right, and then the composition of these subtrees moving them together. Okay, so we can define such an operad, and then so we can define this dendroidal category, it's the full subcategory operads on these objects.
I'll look at the operad.
That would make sense, yeah.
Are all of these finite or
Sorry?
are all trees finite?
Yes, I think I said finance that's somewhere over there, but yeah, definitely. Right, so so this is a definition you can make, but now actually these the operad functors between these things are not as really all that complicated. Like, and like, yeah. Yes.
When you brought up the idea, you mentioned defining free operads. Is there like a difference, but here you're just defining operads. Is there like a difference between free operads and trees and just the operads?
The free operads?
Yeah.
Yeah, this is in a sense the free operad on the tree. And so you can set things up so that there is some adjoint, and there's a left adjoint is unforgetful functor of yeah, it's not really yeah. And this is yeah.
What's the forgetful functor 2 then?
Yeah, that's what I don't want to go into. I can say it in a minute, but it's sort of yeah. Right. Okay. Yeah. So it turns out you can actually describe these maps in terms of similar diagrams to the ones I had here. So if I had a tree, define sum of T in the set of subtrees in T. Then sub star of T in the set of subtrees with marked leaf, so marked incoming edge at the top of the tree. And then I can make a diagram that looks like the one I had for a tree. And if I take the edges of my tree, take sub star of T and then sub T B. Sorry, now here I have a forget the font to forget my marked leaf and sends that to a subtree. Here I have a configure functor that just projects off that marked leaf, and then this functor takes the subtree to its root. To some edge. And so one way to describe that's the omega is that's the same kind of thing over here, just with these things in place of v and v prime. So I have my tree t with edges e and t prime, that is e prime, and I can show mass and that's these kinds of diagrams, and then with this getting a pullback. So a map in omega should send a subtree of t to a subtree of t prime, but the subtree, this pullback condition says that my subtree has to go to one in t prime that has the same number of leaves. And actually, you can simplify this. With this, if I say like this, it's generally compose these things, you stack them on top of each other, but also this data is determined by where I send the vertices in T. So, yes.
Sorry, I didn't mean to interrupt, but I have a quick question. What is the map from sub star to E?
Yeah, sorry. So, yeah, so this is like a subtree T, subtree, I don't know, S with some marked leaf. So I can just forget that marking, or I can just project the
right.
leaf.
Sorry.
And then the last one takes the tree to its root. Yeah, and I'm going, this isn't entirely obvious. I guess you should go and read Joachim's paper for the details. But yeah, so I could describe maps like this. But then this map is determined where I send the vertices in T, because like if I have some subtree, it has to, it has to go to some other condition of the diagram unpacks to tell you that the tree it goes through T prime has to be the one you so if I have a subtree T0 subtree T has to go through that subtree in T prime obtained by gluing together the subtrace I assign to vertices. Okay. Right. So this means that the map is determined by where we send the vertices. And so we can also say this is determined by taking V instead of T prime. Actually, so determined by this diagram. In other words, determined by which subtrees I assign to the vertices. Are you going to ask me like draw a picture of them?
No.
Okay.
I mean, we started with true.
Yes.
And then we created an operads
Mhm.
of, and which is based on the subtrees. And now you're making like a tree from the subtrees.
Yeah, this is not a tree. This is just a diagram, like the same shape. It doesn't satisfy the conditions. Yeah. It's not a tree anymore. It's just.
Is it not?
The leftwards map is not injective.
Yes.
Because an edge can appear as the leaf of multiple trees.
Mm.
But if you want to draw a picture.
Um, In particular, I can think about those maps that send vertices to vertices in this form, like a vertex goes to some subtree, and maybe it's actually just maybe that subtree is just a vertex again. And if it is, I just recover my initial notion of a subtree inclusion. So I can think of the subtree inclusion as a special class of maps in this category omega I defined. So in this case, I'll say that the morphism is in that. And this symbol is active if it preserves the boundary of the tree. So it takes the leaves, and the tree. And so you can try the morphism omega that is uniquely optimized morphism. As an active map followed by a monoid map. Basically, you think of the map as your whole your general map will send the whole tree T to some subtree of T prime. And if that whole subtree is actually the entirety of T prime is active, so you can kind of factor it as the inclusion of the thing the whole tree goes to, and then the inclusion of that into the target. So it's kind of just like an image factorization in that sense.
Yeah. Sorry, what is a morphism of trees? Is it just a commutative diagram or?
Yeah, so it's either you can think of it as a map between these three operads, it's an operad functor, and then I claim that you can identify those as these diagrams that appear. Yeah. So that gives you an alternative description of the category omega. maybe try and draw an example. I can define a map like this. I'm saying that this vertex, it's like really pedagogical and trying these colors. So this life vertex here looks like 3. We just have 2 inputs. That would be say this one. Then this vertex with a single input has to go to a subtree with a single input. We take to the this one. So since this is a nullary vertex, this thing has a single input. And then the yellow vertex, which has 3 inputs, and that's supposed to be assigned to some subtree over here with 3. Here. So the yellow vertex has to go to a subtree with 3 inputs to do this one. And so the mapping condition says that each vertex goes to a subtree, and those have to glue together in the same way as the vertices over here were glued together. So I have to have that the subtree for red and the subtree for yellow has to glue together to the subtree for white. As they do. And then we see this map is neither inert nor active. And to get to factor it, I take the subtree I get by gluing together the full image. So take this subtree of the target, and now my map onto that subtree is active. It takes the root to the root, and it takes the leaves to the leaves. So the 4 leaves here to the 4 leaves of this. Okay, I hope that makes it slightly less mysterious what's going on. Well, I'm actually ready to define this into the Segal spaces. Which are going to be precisions on this category omega satisfying a Segal type limit condition. So I come to this getting sort of a general definition of that. So great tackling. It's an infinity category. Oh, with a factorization system. Not. What's the match? So any morphism factors. As nothing else. Actually, now. So that's the reverse of what I have over here, because here I'm going to really be thinking about omega op as my O. Sort of impossible to pick a convention on whether there should be an op or not that fits all the examples. So, okay, and then we have a collection of elementary objects. Which I think was forming a full subcategory for L instead of O. No, I guess I want to use. Okay, and then given this data, I'm going to find the notion of a Segal object. For this pattern, we need some things to category C.
Sorry.
Yeah.
Is it active inert in the arrow, the ordinary?
It's inert active because my example will be omega O.
Ah, okay, yeah, sorry.
So I easily O equals omega O. But you know, if you take the example we had this morning with finite pointed sets, then I don't have enough of this kind of stuff. So it's sort of yeah.
I didn't say that confusing.
Yes. It just is. I mean, yeah. But it's yeah. So now I want to take this to be an actual function from O to C, not a proof. If such that. But I'm going to oh well. Now, okay, for the communication, I'd say OL X. That's L cross the other that. X energy in X. And X is something that's elementary. Yeah, I was just going to draw the notation such that for every X, given this notation, I can look at the cone on this. Now the pointer from this was cone this last O, and then I can close C, and this should be a limit. That's more explicitly, this is saying that the value of f at x is the limit over the diagram of inert natural elementaries. The value of f on those elementaries. So, in other words, this category, like the inert natural elementaries, tells us how the value of f of this object should be composed as a the example. So we can recover the notion of single space we have at the start of the lecture. And this knew about delta, this was as an active node factorization system. Where map phi and is inert if it's the inclusion of like a sub-interval. So phi I in the phi 0 plot 9. Active is going to zone. Zero, 5, 10. And so this looks a lot like the conditions I had in omega. Like the node is that it's a kind of sub-object and active it preserves the boundary, and indeed you can regard the graphs that are the objects in delta as trees. So I should just mention that. No. Yeah. We just continue the example. So delta up is now the pattern with this stabilization system. And 0 and 1 as a modular object. And then you can check that this definition of a Segal object, the Segal delta object basis is the same thing as the Segal space. We have at the start of the lecture. So the condition of convection, the value of f of n should be the limit over like the category of inert maps from just the opposite side of the inert maps from 1 into n, which is exactly this conclusions, I am 1.5, 10, and then 0 and 10, which are just so this limit condition of actually exactly this iterated pullback that we have in the start of the lecture. Okay, so the point of going through the definition is that now it's easy to state what the dendroidal analog of this should be. So make up this non-gray pattern with our active inert factorization system above. The elementary objects going to be the free edge, which we also call eta, like Marcy did. So this is the tree that looks like this, a single edge and no vertices. And in terms of my definition of tree, it's the tree where I have a single edge, I have no vertices, then go like this. And then I want the corolla with n leaves, because of the tree, that's a single vertex, and n inputs, and then a root. So this looks like I have n plus 1 edges in total, and then n of them are incoming, then I'm on a single vertex, and that includes as well the remaining edge. And then I can say what we from the Segal space. Is a Segal object. Indeed, of free sheet, left from spaces, and then the value of a tree should be the limit over the inert inclusions of corollas and edges, something like. Okay. What does that mean more concretely? So if I take some simple tree, and this one, I have a tree with 3 vertices. And then the condition is that, so that tree is glued from 3 corollas along certain edges, and then I should have a corresponding decomposition of f as a limit of the values of those corollas. So I'll have a nullary corolla that's glued along a single edge to a binary corolla, which is glued along another edge to the order of 3 input. So we have a limit condition like this. So the dendroidal Segal space is a function that takes a tree to a limit, like the value of the tree is a limit according to how the tree decomposes into corollas and edges. So we should think of this as an operad in the sense that, like, the value of f at eta should be a space of objects in the operad. And then the value at the n-ary corolla should be the space of n-ary multimorphisms, so multimorphisms with n inputs. And then I have the inclusion of edges into this, which will like so this limit Segal conditions I'm saying that the value of f of a tree is like a collection of multimorphisms that are compatible so that I can compose them in the shape of the tree E. So in my example up here, the decomposition says that the value of f at that particular tree consists of a nullary operation and a binary operation and a ternary operation, and I can compose them in, their outputs and inputs agree in the sense that in such that I can compose them according to this tree. So in particular, for any tree T, with n leaves, there is a unique active map from CNT, and which gives me kind of a way of composing from F to T to Cn. So I compose my collection given by the tree to a single multimorphism. Right, and then we have a few dendroidal Segal spaces, and then you can again, just as I didn't define for Segal spaces, but again here we can define fully faithful and subjective morphisms. And if we invert those, we can invert those by restricting the full subcategory of complete things. And get them defined, but it's actually the same. Right, I guess I should say this is a relevant consistency in the Maybe finally, I always mention that it's known that this description gives you something equivalent to Lurie's definition of infinity operads. Well, theorem, but Lurie's infinity operads are proven to repeat dendroidal single spaces. Right, so sort of, we want to identify something as a full subcategory of pre-sheaves. So sort of the obvious way to do this is like infinity of omega as a full subcategory of infinity operads. And then I get another functor from infinity between pre-sheaves and omega. And then you just have to check if this is fully faithful with the image frequencies that we go to single spaces. So there's a proof of the theorem that does it this way, which is quite recent due to Inich and Monad. And there were earlier comparisons as well that go through, but they all go through sort of another model. So yeah, so other, maybe I should say the first comparison was via Barwick's model of pre-sheaves. Segal pre-sheaves in a different category, and then Clark compared Lurie's definition to that, and then that they provide only true myself and a third story show that those Barwick's model and the omega model are the same. Okay, I should stop here. Thank you.
Questions for so this completeness condition is it the following? There is a functor from delta to omega of given by the
so
that are linear and you restrict.
Yeah, so you restrict and you get a Segal space, and the condition is exactly that that restriction gives a complete Segal space.
That's it.
Yeah.
Okay.
But then you have to check that that really is still the same thing as being local with respect to fully faithful math, also for opera.
And these are not defined by the.
No, because you also want to say that your equivalence on, or your monomorphism on n-ray operation for everyone. No, but this is still true. Yeah. Yeah.
Do proofs generally get easier when you work in this setting? Could you redo sort of parts of hierarchical by using dendroid spaces?
I think many things get more complicated in this setting. I mean, it really depends what you want to do. And somehow a very nice thing about Operads and infinity operads, there are many different descriptions of them, and that's somehow a useful thing about Operads is that you can look at them so many different ways. So depending on what you want to do, this could be a good way, or there are some people who like to think about Operads as like algebras and symmetric sequences and things like that, and that's useful if you want to do procedurality, but if you want to, I don't know, define the symmetric structure of the spectra, and it's not very useful, for example. Like, it really is important to have all these different pictures, like, depending on what you want to do.